Hello, tune-up and electrical students. I am going to record our first lecture here. We're going to talk about electrical. I'm not going to lie, I'm extra bummed that I'm not in person with you guys right now for this one. This one is one of my favorites to teach, and I feel is probably one of the most crucial sections in this class. Almost as well as any other class you guys will ever take. Electrical is a part of everything, right? Everything runs off of electrical. Everything else in this class, I know we just got done with base engine testing, is going to be heavy on electrical. We're going to be talking about ignition systems, fuel delivery systems, and stuff like that. And everything is ran using electronics. And the further we go, we will eventually get into computer controls and all that good stuff, which again is not possible without electrical. So this is a tough section for everybody, at least most. What I can promise you is that I will be available for any questions that you have for this section. I'm going to try to break this down to its most basic elements and then try to build up from there. A lot of the stuff I'm going to talk about is something that you might find familiar from maybe your Auto 50 class, hopefully. I do sort of try to keep it at its basic level and then bring it back up to like a tune-up level, which we will work our way up to. So we're going to talk about how electricity works, different types of circuits, different types of circuit components. What does a circuit need? Then we're going to get into how to test it. We will get into a little bit of math, so just bear with me. It's going to be very basic math, but there is going to be a little bit, so just say fair warning, as well as the different types of circuits and how to test them. And the reason why we're going to get into a lot of the theory of things is because if you understand how the circuit works, if you understand its characteristics, then you will know what it's supposed to do and what it looks like when it's not doing what it's supposed to do. So I've seen plenty of people out in industry that will poke around a circuit with a meter and really not know what they're looking for. And if they see something that looks bad, maybe zero, maybe that's bad. Is it good? Are you supposed to have zero? Zero what? 0 volts, 0 ohms? What are you testing for? There's lots of questions, and you want to know what you're working with before you start testing it, or else it might as well be the Easter Bunny on your DVOM, right? So we're going to get into a lot of that. I do ask that you be patient because this one is going to be a lengthy lecture. I will try to break it up into 15-minute videos, or around that 15-20-minute videos, so you can sort of give yourself a break in between. Obviously, you can pause and rewind as needed, but just figured I'd throw a lecture out there for this because it's one of those tough subjects. So we'll go ahead and get moving on that. I'm going to screen share with you guys so you can follow along with the PowerPoint here, as long as I can find. Here we go. Sorry, I'm trying to still figure out how to use Zoom here. And now you guys should be able to see what I'm seeing on my computer, which is automotive electrical. And we'll go ahead and go to present mode. You should still be able to see me here in the corner. I'm going to explain some stuff as we go through the slides, and then I will go to the whiteboard as needed. I am going to set a timer for myself here, just so we know where we're at. All right, so now that we are in the presentation, let's go ahead and move forward. Oop, doesn't want to let me. There we go. First things first, back from Auto 50, what is electricity? Well, we know we use it for pretty much everything, but the lights in your house, your phone, obviously your car uses it. Many things in life uses electricity, all of the appliances that you use in your home. So what is it, and how do we break it down? It goes down to the atomic level. So if we're talking about an atom in the center here, like in the picture, it shows a positive sign. I'll explain that in a moment. I don't want to get too crazy into it. This is not a physics class. I want to teach you how to work on this stuff, but I feel like some of the information may be useful. But if you look on the left here on the PowerPoint, it shows a big positive signal in the middle. That middle is going to be our nucleus, pretty much. So if you're familiar with high school science and you remember cells, you probably remember talking about atoms. We've got our nucleus in the center, and then we've got these rings, also known as shells, on the outside that have other particles in them. Well, if we're looking at the center, I know in the picture here it shows a positive sign. That's because we have positive particles as well as neutral particles. So we've got protons and neutrons floating around inside there, but those little particles, what we're really getting at for electricity is those little particles on the outside of the nucleus, on the shells or the rings. We call those electrons, and you'll notice that they have a negative symbol in there. That's because electrons have a negative charge. So what does this have to do with electricity? Electricity is the movement of those negative electrons moving from one atom to the next, obviously at a very high rate. And only certain things allow that kind of electron movement, but that is what electricity is at its basis. As I mentioned, we've got protons, we've got electrons, we've got neutrons. Neutrons have no charge, doesn't matter for this class. And then in the center, we've got the nucleus that contain the protons and the neutrons. Again, our main focus is electrons because that is electricity, is the flow of electrons. I already kind of talked about the layers on the outside. We call it shell, or those layers that yes, I mentioned as shells. The electrons hang out on those shells. And there's different types of electrons or different positions that the electrons can be in. So we can have electrons that are not allowed to leave, that they are called bound electrons. And on the very outermost shell, we call a valence shell. It means that it's the outer one. Those electrons are the only ones that would be considered free electrons to allow movement at all. Right? But depending on how many of those outer shell electrons we have is going to depend on if a material is going to allow that movement or not. Which brings us to the very next subject, which is, well, what do we call something that conducts electricity or allows for that electron movement? We call those conductors. Fancy enough. Well, what makes something a conductor? We know certain things are conductors, certain things are not. You know, water is real good at it. We know that most metals are real good at it, stuff like that. But what makes those materials conduct electricity? Well, something like dry wood or rubber do a really crappy job of it. Well, it all has to do with how many electrons are in that valence or outermost shell of the atomic structure on that material. So for conductors, the reason why it can conduct electricity, stuff like steel, any iron, things like that, copper, gold, silver, all that good stuff, it has to do with its valence electron structure. And it has to have, in order for something to conduct electricity, less than 3 or less than valence electrons or electrons in that valence shell. If it has too many, it can't do it. Think of it like a party, right? So if I've got, or a club or something, if I've got plenty of room for people to come in, then it allows for flow in, right? If I'm throwing a party, I've got tons of room for people to come in. It started as a kickback, now it's a full-fledged party, but I've got tons of people coming in the door, right? Well, if I've got too many people at that party, we're done. We started a cover charge now. We're not letting any more people in. That's a full party. That would be something that doesn't conduct, or in a few slides here, we'll call it an insulator. So the conductor has room for movement, room for electrons to jump on and around. We know the common ones is silver, gold, copper, right? And start to think about what we use for our wiring harnesses. So right here, we've got a conductivity chart from your book. It is a little bit funky. It's supposed to be rated from 1 to 13. But generally starting with the best and then ending down with the least best as far as metal is concerned, right? You can see that normally you would guess, oh, everybody thinks gold is the best conductor. Gold is not necessarily the best conductor. It's a great conductor. Silver, turns out, is going to be your best conductor. The reason for that is its atomic structure. Why don't we use silver? Gold's really good too. It's actually, gold should be number 2, but in our book it shows it as not, copper is number 2. Why aren't we using them? Well, we know that gold's really expensive, so that's a pretty obvious one. But why not silver? Silver's less expensive, still expensive, but really nice stuff. Why don't we use silver? Ask yourself this question: what happens to the silver jewelry that you may own or that somebody you may know owns when they leave it out for a long time? Gets a little layer of tarnish on it, right? And it starts to build up, and eventually you'll get corrosion. So corrosion is what you might have seen on your battery in the car that you have. It's got that, it's that bluish, greenish, whitish, powdery substance, those little chia pets that grow on your battery terminals, or even some household items with AA batteries, right? They even build corrosion on them as well. So you know what corrosion looks like. Well, silver builds up corrosion really bad, really fast. It corrodes actually quite a bit faster than pretty much anything. So unfortunately, if we built all of our wiring harnesses out of silver, we'd have tons of corrosion. We'll talk about why that's not a good thing later on. And then, like I mentioned, gold is obviously very expensive. So what's another really good conductor on the chart that's pretty high up, but may take longer to build up corrosion? Copper. Copper is a really, really good one, and that's why you'll see copper used on a lot of things. On some of the aftermarket harness material that you might see, you may see aluminum being used quite a bit as well, because it doesn't build up the corrosion that silver does. Insulator is going to be the exact opposite. So if you're looking at the picture here, on your left, you'll notice 1, 2, 3, 4, 5, 6 valence electrons on that material. That party's full, right? There's no room for movement. There's no room for anybody to come in and join in. So anything with 5 to 8 electrons in the outer valence shell, it's a full party. There's no room for any movement. There's no room for anybody to come in. So we know common things are going to be plastic, rubber, ceramic. I will mention wood, but it must be dry. Wet wood obviously can conduct. But I mentioned conductors are 1 to 3 valence electrons. Insulators are 5 to 8 valence electrons. So what's 4? Exactly 4 outer shell electrons or valence electrons are going to be what we call semiconductors. Semiconductors, like silicon, germanium, or carbon, are used in a lot of computer control, especially silicon, are used in a lot of computer control applications. What's really nice about semiconductors is I can manipulate a semiconductor to either conduct electricity or not conduct electricity. When you get into an electronics class, you can start talking about transistors and diodes and things like that, where material is used as a semiconductor, meaning something can be used kind of as a switch, or something like that. We will get way more into that in electrical, like a straight electrical electronics class. And Tune Up in Electrical, we try to get really mainly into the actual function of everything. Now that we know about electricity and its properties, well, when I say properties, how it does what it does, right? The movement of electrons. There are 2 different theories. I will tell you, I don't like using the term theory because it's actually been proven that one of them is correct, but in how people look at electricity. The conventional theory is what is known as electrons flowing from the positive side of the battery to the negative side of the battery. And most of you are like, oh yeah, isn't that how everything works? That's what we've been told pretty much our whole lives with anything. But when you really get down to it, it's actually the electron, and I use quotations theory because it's actually been proven on how things actually work. But the electron theory states that electrons actually flow from negative of the battery to the positive side of the battery. Mind blown, right? It's just a little bit different. We'll talk about the term ground and that it doesn't actually necessarily have to mean the negative, but we will get into why the negative is generally used and how that came to be. But those are the two flows. Here's how I want to explain things. As we start, I am going to start talking, especially in this class, as electricity applies to the conventional theory, because it's a little bit easier on your brain since we're already learning a whole lot of new information. We're going to pretend that electrons flow from positive to negative, but I want you to know deep down that Santa Claus is not real. The Easter Bunny is not going to come visit us in a few weeks. The Earth is round. And then that electrons really do flow from negative to positive. But we're going to pretend that all that stuff, that fun stuff, is real for now as we apply it to theory stuff. But when you get into an electrical class or an electronics class, they are going to start talking about things as they apply to real life, which is negative electron flow to positive. So let's get into the meat and potatoes of terminology here. So we're going to measure, we're going to do a lot of measuring of electrical components in this class. We're going to try to figure out if a component is bad, if there's a fault in the circuit, stuff like that. And how we know that there's faults is using units of electricity to measure things. So much like you would measure the distance of something, we're going to measure how much volts, amps, or ohms things have. So what do those terms mean? The most common one you'll probably hear is voltage. In physics or in your book, it may refer to this as electromotive force. This is an automotive class, and I will tell you that nobody in the field have I ever heard call voltage electromotive force. Again, this is not an engineering class, so we'll know that that term means that. So when you see it in the book, electromotive force is referring to voltage. But what is voltage or electromotive force? It's actually the pressure. So I mentioned that the electrons or electricity is the movement of electrons from one atom to the next, to the next, to the next, to the next, right? Well, how come any metal material isn't always conducting electricity? Well, we have to have some sort of reason for it to move, a push, if you will, and that is voltage. So voltage is going to come from a battery, some sort of power source that is going to provide a pressure. We need to coerce those electrons to actually move, and that's what voltage is. It is not the movement of electrons. It is simply electrical pressure. Simply like a water pump or any kind of pump that is, it's not the fluid itself, it's simply pumping pressure, and it's using the fluid in a system to pump pressure. That's voltage. It's simply electrical pressure. Now, when we get into the actual electricity portion of it, we know that it's the movement of electrons. So that is what we're actually going to call amperage. Amperage is electron flow, or the flow of electrons. In your book, it will probably call it intensity. I'm going to throw that right there with electromotive force. And this class, we won't be referring to amperage as intensity because in the field, more than likely, you're going to hear the term amperage. I will be using the term, if you look here on the left, it says AKA current or intensity. Current is another one that's very commonly used in the field. So I'm going to use the terms amperage and current pretty synonymously. They are the same thing. Current is electron flow. Amperage or amps is electron flow as well. So the picture you have here is an ammeter. It's simply a really fancy electron counter of electrons moving past. So we know that amperage is the actual electron flow, or the flow of electrons moving from atom to atom to atom to allow this to create electricity, right? Excuse me. Voltage is what's pushing those electrons, acting as an electrical pressure. So now that we know those two terms, what's our third, and why would we even have amperage or voltage? There's something called ohms. And ohms is pretty basic. It's actually, this term is used across the board. I may call it resistance, but resistance, ohms are going to mean the same thing. So circuits have to have something to do. There's got to be a reason for us to use electricity, right? I'm turning on a light, I'm spinning a motor, I'm creating heat or movement, whatever it might be. That is going to be resistance. It's going to, you can think of it like working out. You work out with a weight, right? You're doing something, that weight is going to be your electrical resistance or whatever it is that you're doing, right? So the electrical resistance can either be on purpose or on accident. The on purpose ones are the ones that we turn a light switch on to turn on a light, right? I honk my horn, I expect my horn to honk. The accidental ones are ones where I build up corrosion inside of the circuit, or I have an electrical component that is faulting and is creating electrical resistance on accident. So those are the three terms we're going to use over and over and over and over and over again. So if you didn't get that, pause, rewind, watch the last few minutes again, because you need to understand volts, amps, or ohms. If you have any questions on that, please message me. There is one more, but those three are the ones that we're going to measure. This next one we're not going to measure, but I do want you to know what it is because we're going to use this term a lot. And that's watts. So what is watts? I know a lot of you guys have heard of a watt. When you buy a light bulb, it has a wattage rating on it. You've heard the term watts some point in time in your life. Well, what the heck is watts? Watts is the capacity to do work or work being done. It's also commonly known as power. So power or work being done, that is what watts is. What is actually being done? If you want to calculate watts, it's actually really easy. You take voltage, you multiply it by amperage, and that will give you how much work is actually being done. Hopefully I'm looking at my video and it's showing it a little bit backward, but hopefully you guys can all see that. Watts equals amps times volts. And that's your equation on how to calculate watts, if you want to know how. I'm also going to show you guys a couple of other equations on how to calculate some things, at least get a rough estimate of what's going on. And this is me being cheesy. Sherlock Holmes and Dr. Watson. All right, now one more thing before I get into the next subject, and I'm probably gonna start another video, is the units and symbols used. So right here in the picture, I did mention a moment ago that we will only be measuring 3 units, and that is voltage, current, and resistance. So when you are measuring voltage, the symbol that's going to get used is V. And I'm going to stop screen sharing here. Take a look real quick here, the resistance. It's a little omega symbol. Current, we use A, and V, we use voltage. I'm going to stop screen sharing here because I'm going to show you something here on the whiteboard. So if I look at a number, let's say I just measured voltage and I got 12 volts. That's pretty easy to read, except for I think you guys are seeing what I'm writing backwards. We'll see when I double check my video. If I am measuring amperage and I get 12 amps, I can either use lowercase or I can use an uppercase A. Either way, no big deal. But it's very easy to see, 12 amps, 12 volts. Well, if I measure ohms, the reason why we use a symbol for ohms and not necessarily just a letter, because why not just do 12O, right? Well, here's the problem with that. That looks an awful lot like 120, doesn't it? So that can get a little bit confusing. And I'm sure there may be other reasons, but for the most part, every time you express ohms, it will be using the omega symbol. So instead, it will be 12. And the omega symbol is pretty easy. Straight line, almost circle, and then another straight line. Most of my omega symbols from here on out are going to be really lazy and look like this, like maybe a baby octopus. But that's the symbol we're going to use for ohms. A for amps and V for volts. So I'm going to go back to our screen share here just to see where we're at. I think we may start another video here in a moment. Actually, real quick, I do want to explain this before we sort of get into the next video, and that is the relationship between these units. So all of these units actually have a little relationship you can think of. It's like a little love triangle, right? Resistance and amperage have the most important relationship, while voltage and amperage, also very important, is not going to apply to you unless you're changing what type of vehicle you're working on. And actually, let me see here. I'm gonna explain this, and then we're gonna get actually into Ohm's law when I come back. So I really want to explain this real quick here because it's such a key subject. Such a key subject. First things first, the reason why I'm explaining this to you guys is because if you understand this, you will understand diagnosing so much easier. Explaining that is going to be so much easier. And knowing the basis of how something works is going to make you a better diagnostician. So, two relationships. We've got resistance and we have amperage. Their relationship is very much like a teeter-totter. So if I've got a little teeter-totter here, right? Everybody knows since you were a kid, well, that's not really equal here, that a teeter-totter, well, one person goes down, the other person goes up, and vice versa, right? It moves back and forth. That is what resistance and amperage do. So I've got ohms on one side and amperage on the other. While one goes up, the other comes down. That is their relationship. One of these must control this though, right? Which one controls which? Which one has the control in that relationship? In this case, it's going to be ohms. Ohms is going to control your amperage flow or your current flow, your electron flow, right? So the more resistance I have, what will start to happen is the amperage or electron flow will go down. The less resistance I have, the more amperage or electron flow we have. And that is a key relationship, because when I have faults, when I have a low amperage or low current flow fault, that means, if I have a low resistance fault, meaning something happened and shorted the resistance in the circuit, and I have low or no resistance, that means amperage shoots up, and that's a problem. Too much amperage is a problem. There is such a thing. In fact, we'll talk a little bit about how that works and why that happens, and what symptoms that might cause. Because high amperage could mean fire. It means heat, a lot of flow, too much electron flow for the circuit to handle. High resistance faults, on the other hand, have the opposite problem. Not enough current flow to do the job. We'll talk about how that happens, but this is such a key relationship for you to understand because it's going to help you diagnose later on while you're actually working on stuff. Amperage and voltage have a very different relationship, but yet again, amperage sort of takes a back seat to things. So voltage and amperage have a relationship as well, except their relationship, instead of a teeter-totter, is very much like an elevator together. So we've got voltage standing next to amperage on an elevator. When one goes down, the other goes down as well. When the other goes up, or when one goes up, the other goes up as well. Again, amperage takes a back seat. Voltage is the one that's making all the calls here. So when voltage or pressure, think about that pressure and think about fluid in a system being pumped. The more volume, more pressure that pump is pumping, the more of whatever it's pumping is coming out, water, transmission fluid, whatever it might be, right? That is your voltage. Voltage is controlling the pressure. Well, if I have low pressure, I'm going to have less flow. If I have high pressure, I'm going to have higher flow. Now, here's the issue. We're going to get into continuity. If I don't have any of this at all, it doesn't matter what voltage is. I can have all the pressure in the world. If it's not pushing anything, it doesn't mean any difference. But this is how their relationship between voltage and amperage works. I'll talk about how a circuit has electron flow and all that good stuff. But in this case, the way you can think about this is like a 12-volt system on a car versus a hybrid battery, something that's, I don't know, 240 something volts, whatever it may be. The reason why hybrid vehicles are so dangerous is not because of the level of voltage. You can get shocked with thousands of volts. People do it all the time on ignition systems. You might pee yourself a little bit. It's going to hurt, but you're not going to die. So what is it that kills people when you get electrocuted? It's amperage. So here's the problem. Little bits of voltage pushing little bits of amperage, not that big of a deal. If I've got something like a 12-volt system, I can lick my fingers and touch positive and negative, and I am not going to create enough amperage flow to die, even though I'm still getting that 12 volts. But a hybrid battery, I would die before you could say die. It happens very quickly. And the reason for it is not only do we have an increase in voltage in a hybrid battery, but we also have, because of the increase in voltage, we have an increase in amperage, and that's only a power flow, or I'm sorry, a power source thing. So if a battery has more voltage, it will have more amperage output. If I have something like an ignition coil where I'm upping my voltage via transformer, if I'm speaking another language to you, don't worry about it. I'll explain this later when we get into ignition systems. But if you know what I'm talking about, you are not going to get the same amount of amperage. But we'll get into that later. So you don't die from getting shocked from an ignition system because it has a lot of voltage but not a lot of amperage. But from a power source, like your actual battery, if I up the voltage from my battery, I up the amperage flow as well. So just something to think about. I know it's sort of a lot. I'm going to go ahead and end the video here, and I'm going to start the next section. If you're ready, follow with me. If not, you may need to watch a couple of moments of that last lecture again, but I will see you in the next video.